Hi everyone. So this video is going to be an introduction to the video on Bessel equations that I recorded earlier. So I recorded almost an hour of content, and I'm not satisfied with the way that I did that because I don't think I did a good job of explaining the motivation for everything that we were trying to do before I recorded that video. So I want to go back through some of the big thematic ideas we've hit so far and connect it up with what we're going to be doing in the section about Bessel equations. So in the section on series solutions, we showed that if an equation had an ordinary point, then we could assume that the solutions to the equation were a series. So what we showed is, specifically, is that if we have a differential equation that looks like y prime prime plus p of x y prime plus q of x y is equal to 0, and we're at a point x is equal to a, such that the functions p of x and q of x are analytic at x is equal to a, we were allowed to assume that this function had solutions that were power series. y1 of x was equal to the sum from n is equal to 0 to infinity of an x to the n, and y2 of x was the sum from n is equal to 0 to infinity of bn of x to the n. And once we had those solutions, then we found immediately a very important type of differential equation that we could solve with those series solutions, a differential equation that arose in physical applications. So first we developed a technique based on an assumption about the behavior of the equation, and then we solved a specific equation with the objective of examining its solutions. The particular equation that we solved was called Legendre's equation. Legendre's equation shows up in many physical applications, and the equation itself is 1 minus x squared y prime prime minus 2xy prime plus alpha times alpha plus 1 is equal y is equal to 0. So first we developed a technique for solution, then we applied it to an equation, and the consequence that we got from applying the series method to that equation was a family of orthogonal functions called the Legendre polynomials, Pn of x, that have the property that Pn of x is orthogonal to Pm of x for the inner product Pn Pm is equal to the integral of Pn of x times Pm of x dx. And then with the inner product, we were able to use ideas from linear algebra to show that we had an expansion theorem. And what the expansion theorem said was that as long as we were between -1 and 1, which is where this inner product is defined, then any function f that we wrote down that had f and f prime, both continuous, had an expansion in terms of Legendre polynomials. That is, f has a unique expansion n equals 0 to infinity of Cn Pn of x, where each Cn is computed as a dot product, the dot product of f against Pn over the dot product of Pn with itself. So the four things we did were we developed a method of solution, we applied it to a specific differential equation arising in physical practice. From that, we had a specific set of solutions that came out of that were orthogonal with respect to an inner product. And then we got an expansion theorem. So what we're doing right now is we're building the same sort of set of ideas, but with Frobenius series. So here's where we are with Frobenius series. 1. We developed a method of solution to a specific form of differential equation that looks like x squared y prime prime plus p of x times x y prime plus q of x y is equal to 0, where p and q are analytic at x is equal to 0. Solving this kind of equation, what we've shown is that we can use a method called Frobenius series. So this is sort of 1a, right? We've got this type of equation. What is the method of solution? Well, the method of solution of this equation was to write down that y was equal to x to the r1 times the sum from n is equal to 0 to infinity of an x to the n. And then whatever y2 was heavily dependent on certain extra factors, right? But the idea was that at very least, I know that this solution exists always, where r1 is a solution to the equation r times r minus 1 plus p naught r plus q naught is equal to 0. So we've built a general equation and a method of solution for that general type of equation. What we want to do now is to see what we get access to that comes from the physical world now. What new equation can we solve with this method? After all, in the previous section, when I had ordinary points, that got me access to Legendre's equation. And when I had Legendre's equation, I could use it to develop a family of orthogonal functions and show that we had a basis for an infinite dimensional vector space of functions, an expansion theorem. I want to do exactly the same thing here, which means that I need to write down a specific equation and the equation we're going to be looking at is called Bessel's equation. Which shows up when you're trying to solve a Laplacian from physical systems. So spherical harmonics are one context that you see this in. Once we have a specific equation, we're going to look at, hopefully, a family of solutions. Because if I can find a family of solutions to that differential equation, I can express, hopefully, any function in terms of the physical setting that that differential equation sets up. Okay, so we're going to get a family of solutions, and what we hope is that these things are orthogonal. And a basis for some space of functions with regard to some inner product. And I'll give the hint here is this time we're going to have to use a slightly different inner product. The inner product of two functions f and g in this case is going to be defined as the integral of x f of x g of x. It still follows the rules of a dot product. It just has this x in here, which is called the weight. So we have a different dot product, but the idea is going to be the same. We're going to start with a specific equation, which looks like x squared y prime prime plus xy prime plus x squared minus alpha squared y is equal to 0. So that is the specific equation we're going to use. We're going to build a space of functions with this inner product, and we'll show that a specific family of solutions to this specific differential equations is an orthogonal family. And then the crowning jewel is we're going to be getting an expansion theorem, hopefully. So just as in the case of series solutions and the Legendre polynomials, I want an expansion theorem. That is, I want to be able to express any function in terms of solutions to a Bessel equation. You might think, well, why? That's great that you want to do this parallel thing where you had step 1, where you showed a method of solution for a general type of equation. Step 2, where you wrote down a specific equation and looked at the answers. Step 3, where you showed they were orthogonal with respect to some inner product. And step 4, where you gave an expansion theorem. Fine, I buy that. You want to write down a specific equation, you want to examine the family of solutions, and then hopefully at the bottom you get an expansion theorem. But why? The answer is partially contained in the talk that I gave on linear algebra in infinite dimensional spaces, which is an optional video, but I'm going to pull over here why you might want to do that. In the demo that I did in MATLAB on functions as vectors, the specific thing that I want to look at is how Legendre polynomials work in terms of the practical application of the expansion theorem. So if we take a function, say, like e to the minus x squared, and we develop an expansion of that function or an approximation of that function in terms of Legendre polynomials, I get a near perfect approximation. So the first graph that you should see in here is the graph of e to the minus x squared. This is the graph of e to the minus x squared with the graph of a degree 10 approximation laid over the top of it. Essentially perfect. So my expansion theorem says that I could approximate if I had infinite terms, but the approximation part of it says we'll clip off after 10 or 12 or 14, and it's basically perfect, which is awesome. Except polynomials are good at approximating things that mostly look like they behave like a polynomial. Once you start getting into functions that have periodic behavior or functions that are discontinuous, then polynomials are not good approximations anymore because polynomials are unbounded. Polynomials, as you head to infinity and minus infinity, tend to explode. And you can see that if you look at an approximation for a square wave using Legendre polynomials. So here's a square wave. And just naively using the same exact expansion for Legendre polynomials, you can build an expansion for this. And an approximation's pretty close. Except, once you get too many terms in the polynomial, you end up with powers that are so high that small errors end up sending the function off to positive infinity and negative infinity. And you can see that over here. These are places where that approximation breaks down very badly because polynomials are not good at approximating periodic functions. So why would we possibly want to deal with an expansion in terms of functions coming out of a wave equation? And the answer is, if the solutions are solutions to a wave type equation, then they're going to model periodic behavior. And it's going to be a fortuitous happenstance that when we go back to our expansion theorem for the specific differential equation that we're going to look at, which is Bessel's equation. Remember, the Bessel's equation comes from studying waves, spherical harmonics. The solutions to this equation are going to turn out to be an orthogonal system of functions that we can have an expansion theorem for, but those functions will all be bounded and they're going to oscillate. So the result of this expansion theorem is we'll get expansion in terms of bounded oscillating functions. And expansions in terms of bounded oscillating functions means that we can model bounded oscillating functions much better than we can with polynomials. So that's the big top level view of why we're working on Bessel equations at all. And then the video that follows this kind of takes the opposite tack, where it starts at the base level. It starts with the nitty gritty and then builds up to the end. The one thing to keep in mind is I recorded this video second after I recorded the first video and I was unsatisfied with the explanation of what's going on in that video. So think of this as the introduction and the next video as a video about technique. All right, so that's what I want to say about this. Bessel functions are great. Their expansions are awesome. The second video, it's going to be more technical, but the details are important. And then we'll talk a little bit about some properties that Bessel functions have when we get there. All right, so take care.